So coming to the chemical properties of these group 16 elements, we start with hydrides. Hydrides of group 16. Group 16 elements forms hydrides of this type, where X, this is the central atom, and this the central atom X, this undergoes sp3 hybridization. The number of bonded pair, we have 2 bonded pairs and 2 lone pair. Now these sp3 with only 2 bonded pair, geometry is tetrahedral, but the shape or the structure will be bent or angular shape. We say this is due to the lone pair repulsion. So we have these hydrides. So the central atom X of these group 16 hydrides undergoes sp3, and this shape is bent or V-shaped or angular, but the geometry will be tetrahedral. Now since due to this lone pair repulsion, bond angle will be less than the theoretical value of 109.5. So coming to the hydrides, we have H2O, H2S, H2Se, H2Te. So these are the hydrides. We are excluding the hydrides of polymeric, that being the radioactive. So we have the hydrides of this. Now we'll discuss the properties of these hydrides. Now first we'll discuss XH bond length. Now moving down the group, the size of central atom increases, but the size of hydride remains very small. So as we move down the group, the size between central atom and hydrogen increases. As the size increases, the overlapping tendency decreases. As a result, the bond length increases from H2O to H2E. So bond length of XH bond increases due to increase in size difference. So due to increase in size difference, bond length increases. Now as the bond length increases, the bond energy, as the bond length increases, bond strength down the groove decreases. So bond strength is inversely related to bond length. If bond length is more, bond strength is less. That means the bond energy of this XH bond down the groove will decrease. Now look at this. If the bond energy decreases, or bond strength decreases, or bond length increases, then the stability of these oxides, hydrides, it means thermal stability. So stability of these hydrides decreases down the group. So the most stable hydride is H2O. Now coming to acidic behavior, acidic nature. Now look at this, moving down the group, the strength of the bond length increases, or the bond strength increases, or the bond energy decreases. Now as the bond length increases or the bond energy decreases, the stability of this XH bond decreases. As the stability decreases, the tendency to break this bond increases. So the acidic character increases from H2O to H2Te. Now all this can be explained based on this stability of central atom hydrogen bond. Now if you look at this, when we compare the boiling point of these elements, The boiling point follows the order. H2O is the one having the highest boiling point, followed by H2TE, followed by H2SE, followed by H2S. So this from sulfur to selenium to tellurium, boiling point increases because size increases. As the size increases, the intermolecular attractive force increases. So means as the size increases, surface area increases. Due to increase in surface area, the intermolecular attractive force increases as the boiling point increases. Whereas in case of the smallest size H2O, the boiling point is a maximum. So this is due to intramolecular hydrogen bond. Intramolecular hydrogen bond. So due to this, the intermolecular attractive force is through stronger hydrogen bond. So to break this bond, we require larger amount of energy, hence the boiling point. If this is the boiling point, then the volatility will be just reverse. So H2 is the least volatile, followed by H2E, followed by H2SE, followed by H2S. So this is the one having most volatile, means the least boiling point. So this is hydrides. Now coming to the variation in bond angles. Bond angles. The force force compound that is H2, the bond angle is 104 degree. This is 92.5, this is 91, and this is approximately 90. Now for the first case H2O, the bond angle is close to the tetrahedral angle, that is 109, but the value is less than 107. So we explain this is due to lone pair repulsion. So we have looked at it. This is oxygen, we have this hydrogen, and this has got two lone pair electrons. This lone pair undergoes lone pair repulsion. So the lone pair repulsion being the one having maximum value of repulsive force. So this, because of this repulsion, this bond angle will slightly decrease. So due to this bond angle comes to be less than 109, which is approximately equals to 104. But if you look at this, for the rest of the elements, the bond angle is very close to 90 degree. When we say the bond angle is very close to 90 degree, the concept of hybridization is less prominent. So hybridization is most prominent in this case. Hybridization is less prominent, meaning thereby pure p orbitals are used in bonding. Now since pure p orbitals are used in bonding, the bond becomes weaker. As the bond becomes weaker, bond strength decreases or bond length increases. So in this sulfur selenium tellurium hydride, there is involvement of pure p orbitals of the central atom for bond formation with the hydrogen. Whereas in case of water, this central atom oxygen uses is hybrid orbitals to form bond with the oxygen. So the bond formed by hybrid orbital is stronger than the bond formed by pure atomic orbitals. As a result, these hydrides are less stable when compared to that of oxygen. So this being less stable, bond length is more, bond strength is less, bond energy is less. So this is about the hydrides of this group 16. Now coming to next, that is, we'll discuss the oxides. Oxides of group 16. Now these oxides, we classify these oxides into various ways. First, based on structure, Based on the structure, this is classified as normal oxide, and this has got the structure O2 minus normal oxide. Example, Na2O, K2O, BaO, MgO, etc. These are known as normal oxide having this O2 minus. The other oxide is peroxide. We have O2 2 minus, so the oxidation instead of oxygen is -1 in case of peroxide. So this is 2 negative charge for 2 oxygen, so per oxygen is -1. Example, we have Na2O2, BaO2, we can H2O2, H2, SO5, etc. These are peroxide and this contains peroxides. Then we have superoxides. Superoxides has this O2 with -1, so per oxygen is -half. We have these examples. KO2, RbO2, etc. Now we can also have suboxides, and the best example is C2O3 carbon suboxide. We have this. C3O2, this is carbon suboxide. This is based on structure. Based on chemical nature, these are classified as neutral oxides. So neutral oxides means this oxide does not show acidic as well as basic behavior, or we say this oxide does not react with acid as well as base. So we have this example: carbon monoxide, nitrous oxide, nitrogen monoxide. These are neutral oxides. This does not react with acid as well as base, or means does not show acid or basic property. Then we have acidic oxides. So when we say acidic oxides, so these oxides shows acidic behavior. So generally non-metal oxides are acidic in nature. So we have Cl2O7, we have N2O5, we have N2O4, we have P2O5, etc. So these non-metal oxides, we can also have, look at this carbon dioxide, we can have SO2, we can have SO3, etc. These non-metal oxides are acidic in nature, means when these are dissolved in water, that gives you acid. So these are known as acidic oxide. Then we have basic oxide. So metal oxides are generally basic in nature. So we have Na2O, K2O, BaO, MaO, calcium oxide, etc. These oxides, when dissolved in water, gives you hydroxide ion. Since they furnishes hydroxide ion, these oxides are known as basic oxides. Then we have amphoteric oxides. So these are the oxides shows dual property. They shows acidic as well as basic property. So these oxides shows both acidic as well as basic property. Now the metal oxides of p block elements shows amphoteric in nature. So we have Al2O3, we have lead oxide, we have tin oxide. So these oxides shows both acidic as well as basic properties. So these oxides are known as amphoteric. So we can have a number of combination of this oxide. Now coming to this oxide, peroxide and superoxide, let me just compare the values. So look at this, we have this take this potassium oxide. When dissolved in water, this gives you potassium hydroxide. So this potassium hydroxide being ionizable, this furnishes potassium ion and OH. So this OH minus formation is the reason why we are saying this potassium oxide is basic in nature. Take this potassium peroxide. When this is dissolved in water, we say this potassium oxide plus hydrogen peroxide is formed. Now this hydrogen peroxide, this is a very good oxidizing agent. So since hydrogen peroxide is a very good oxidizing agent, so these peroxides, all metal peroxides are very good oxidizing agent, because when these are dissolved in water, this furnishes hydrogen peroxide, which is a very good oxidizing agent. So this is also basic because of formation of this hydroxide ion. Then take this KO2, potassium superoxide. When this is dissolved in water, this furnishes potassium hydroxide, and this formation of potassium hydroxide is responsible for this basic character. Along with this also furnishes hydrogen peroxide along with molecular oxygen. So in both the case, look at this potassium peroxide and the superoxide, both furnishes hydrogen peroxide, so both are oxidizing agent. But when we compare the oxidizing character of peroxide and superoxide, superoxides are stronger oxidizing agent due to the formation of additional oxygen. So oxygen itself being a oxidizing agent, so this is stronger oxidizing agent. So this potassium peroxide is stronger oxidizing agent. So why this is more stronger oxidizing agent? Due to the formation of oxygen, additional oxygen, which itself is acting as an oxidizing agent. So when we compare the oxidizing property of this peroxide, superoxides, so superoxides are stronger oxidizing agent than the peroxide ions. This is the reason. Now coming to next, that is oxo acids or oxoanionic acids. Oxo acids of these group 16 elements, and in this oxo acids we'll discuss the oxo acids of sulfur. Oxo acids of sulfur has got different series, so we'll take up one by one. Oxo acids of sulfur. The first one is sulfurous acid series. Sulfurous acid series. In this sulfurous acid series, we have this series of acids. we have sulfurous acid, that is H2SO3. The oxidation state of sulfur is +4. Structure is either this is the proposed structure or this is the proposed structure, because some of the properties of sulfurous acid is explained by this, some of the properties are explained by this. Sulfurous acid forms two series of salts, so we have this. Sulfurous acid shows reducing property, and that reducing property is shown by this hydrogen, which is directly attached to the sulfur. Then we have Pyrosulfurous acid. So Pyrosulfurous acid is H2O5. The oxidation state is, this is again +4. Structure this is the structure of Pyrosulfurous acid. This acid has got two ionizable hydrogen, so N factor is 2 here. Then we have Thionic acid with formula H2H2O4. The oxidation state is +3, average oxidation state. So we have H double bond O, H double bond O, OH, OH. So this is sulfurous acid series. So under this sulfurous acid series we have three acids: sulfurous acid, pyrosulfurous, and thionic acid. The second series of acid is sulfuric acid. Sulfuric acid series. In this series we have acids sulfuric acid H2SO4. Structure is this is the structure of sulfuric acid, and this contains two ionizable hydrogens, so these forms two series of acid, and the oxidation state is +6. Then we have pyrosulfuric acid. So pyrosulfuric acid formula is H2H2O7, still oxidation state is +6. Structure is 2 sulfuric acid units joined through a common oxygen, that is pyrosulfuric acid. Ionizable hydrogen is 2, so the acidic character or the N factor is again 2. Then we have thiosulfuric acid. So in this, one of this oxygen of sulfuric acid is replaced by hydrogen, so the formula is H2H2O3, and this sulfur has got two different oxidation states, so I'll show you the different oxidation states. So we have this sulfur, and one of these oxygen is replaced by sulfur. So because of this, this is known as thio. So if you look at this sulfur is +6, this sulfur is -2 oxidation state similar to the oxide, and these hydrogens are ionizable, so the N factor for this acid is again 2. This forms sulfuric acid series. Now next series of acid is Peroxo acid series. Paroxy acid series. This contains peroxide bond. So under this peroxide acid series we have two different series. Pyroxy mono sulfuric acid, which is also known as Keros acid. The formula is H2SO5 and the structure is, I'll show you the oxidation state also. HO, sulfur double bond O. So we have this peroxide bond. So due to the presence of this peroxide bond, this is known as peroxo acid, and this is, we have a single unit of sulfuric acid, so peroxo monosulfuric acid. So this peroxide is having -1 oxidation. This is normal -2, normal -2, normal -2. So the oxidation state is +6 here. So sulfur is in +6 state, but this contains a peroxide bond, and the peroxide oxide is having -1 oxidation state. The second acid is Paroxy disulfuric acid, which is also known as Marshall's acid. The formula of acid is H2H2O8. Structure is HO, sulfur double bond O, double bond O, OO. Means between two sulfuric acid there is a peroxide linkage. Peroxide linkage. The oxidation state is again +6 here, +6 here. This is -1, this is -1. So this is the average oxidation state. And the final is Thionic acid series. Thionic acid series. First one is dithionic acid. Formula is H2H2O6. That is dithionic acid. The formula is dithionic acid, and if you look at the structure, there are two ionizable hydrogens, so the acidic property shown by this series n factor by 2. If you look at this, n factor is 2 here, n factor is 2 here. Oxidation state is, if you look at it, this is -2, so -12 plus 2, 10, 10 by 2, 5. Each sulfur is having +5 oxidation state, that is the average oxidation state. Then we have polythionic acid. We have H2SNO6. So we have this structure. So we have this sulfur in two different oxidation state, and this sulfur, which is the place in between these two groups, this sulfur is always in 0 oxidation state, and this sulfur is +5. This is also +5. So we have two sulfur. So this is the only this acid contains sulfur linkage. So these are the various series of peroxy acids of sulfur, and in this peroxy acid series we have to remember the name of the compound, acid, oxidation state, number of ionizable hydrogen, structure, and if the acid contains peroxide linkage or if the acid contains sulfur linkage. So all these are important from examination point of view, and you have to keep in mind. Now in this, along with this acid series, we'll discuss one of the most important acid of the sulfur is sulfuric acid. So we'll discuss this sulfuric acid. So coming to sulfuric acid, H2SO4, first we'll see the preparation of this sulfuric acid. So the preparation of sulfuric acid is by a process known as contact process. Contact process. So the steps involved is, first we have this sulfur. The sulfur is burned with oxygen when this is converted into sulfur dioxide. In the second step, this sulfur dioxide reacts with oxygen gas, and this develops an equilibrium to give you sulfur trioxide. So this is gas, this is gas, this is gas. This takes in presence of catalyst vanadium pentoxide V2O5, and this is one of the most crucial or the most important step for this. This reaction is, look at this, the formation of sulfur trioxide from sulfur dioxide and oxygen. This is an exothermic process. Since the reaction being exothermic, this reaction should be carried out at low temperature. After formation of this, look at this sulfur trioxide, the partial pressure of gas decreases. As the partial pressure decreases, this reaction must be carried out at high pressure so that the reaction is shifted in the forward direction, or the quantity of sulfur trioxide increases, or the yield of sulfur trioxide increases. Third, the reaction must be carried out in presence of large excess of oxygen so that this reaction is converted into the product side. Fourth, the sulfur dioxide and oxygen used in this must be free from impurities. If there is impurity, then that impurity will poison the catalyst. As this poisons the catalyst, the product formation will be decreased. So these are the three important points. So for this, one is reaction should be carried out low temperature, reaction should be at high pressure condition, so reaction should be in excess of oxygen gas, and the reaction should be oxygen gas and the sulfur dioxide should be free from impurities. Free from impurities. So in the third step, this sulfur trioxide is dissolved in concentrated sulfuric acid when this gives you H2S2O7, that is oleum. And finally, this oleum is hydrolyzed by adding required amount of water when this gives you the sulfuric acid. So this is how we prepare sulfuric acid by contact process, and this step is a very crucial, very important step, and for this we have to remember this thing. Now we look at this is an acid. To this being an acid, this will show all the properties of acid. This will easily react with base, so I am not giving any acid base reaction. This will react with any of the base or the basic compound to give you salt. So that is normal acidic property. Apart from this acidic property, this sulfuric acid also shows oxidizing property. Oxidizing property. The oxidizing property of this sulfuric acid is H2SO4, that is hot and concentrated solution, gives you H2O plus SO2 plus active oxygen is formed. The formation of this active or nascent oxygen is responsible for this oxidizing behavior. So this shows very strong oxidizing, and as we look here, sulfur is in highest oxidation state, so this will always show oxidizing property. When sulfuric acid is acting as an oxidizing agent, the product form is sulfur dioxide, that is lower oxidation state, plus 4. Now this can oxidize non-metals also. Metals can be easily oxidized, but non-metals can also be oxidized. So look at this. Carbon when react with this concentrated sulfuric acid, this gives you carbonic acid plus water, etc. These can oxidize phosphorus also to give you phosphoric acid plus SO2, etc. So these non-metals can also be oxidized by this concentrated sulfuric acid. But when we react with metals like zinc sulfuric acid, so this gives you zinc sulfate and hydrogen gas is released. So zinc is changing from 0 to +2. Similarly, we can have a look at this iron plus sulfuric acid. When this gives you iron sulfate plus hydrogen gas is released, we can take this aluminium with sulfuric acid. When this gives you aluminium sulfate plus hydrogen gas is released. So what these electropositive metals react with this sulfuric acid to give you metal sulfate and hydrogen gas is released. But when this is acting as an oxidizing agent, it reacts with non-metals and this produces sulfur dioxide. And this sulfur dioxide gas is the gas which is used for conversion into sulfur trioxide, which is used for preparation of sulfuric acid. So this is some of the oxidizing property that I have explained you why this is acting as an oxidizing agent. Look at this. This sulfuric acid is also acting as a dehydrating agent, that is removal of water. In many of these organic reactions, what sulfuric acid is used as a dehydrating agent. Take this reaction. We have alcohols on heating with sulfuric acid concentrated. This releases to give you ether, or this reacts to give you alkene. In both the case, water is removed, and this is at low temperature below 140, this is temperature above 140. In both the case, there is a dehydration to give you different product. Similarly, this, when we react with this glucose or fructose C6H12O6, this is either glucose or fructose. This reacts with concentrated sulfuric acid and this gives you carbon solid plus water. Sugar charcoal is formed. So in nitration reactions also we use this benzene plus nitric acid plus sulfuric acid. In this acts as an acid and helps in removal of water molecule by formation of hydronium, and when this gives you nitrobenzene. So these are some of the properties of sulfuric acid. To this sulfuric acid, the oxo anion, let me give you the structure of this. H2SO4, this ionized to give you H++ SO4. Suppose the force ionization constant is K1. This HSO4 minus ionized to give you second H+ ion gives you SO4 2 minus. This is second ionization constant. Now the force ionization constant is always greater than the second ionization constant. The reason being that after the elimination of force H+ ion, this H+ ion is acting as a common ion effect for the second equilibrium, and because of this H+ ion acting as a common ion effect, this second ionization is less, Hence, the first ionization constant is always greater than the second ionization constant. So look at this. This in the first reaction, this is acting as a base. If this is acid, this is conjugate base. In the second reaction, this is acting as an acid. So this is the same species, HF4 minus. In one of the reaction, this is acting as a base. In one of the reaction, this is acting as an acid. So this is what we call as amphiprotic ion. Amphiprotic ion. So coming to this sulfate SO4 2 minus, this is undergoing sp3 hybridization tetrahedral. So we have this sulfur oxygen. Now this undergoes resonance stabilization, and now look at this. This sulfuric acid, the oxo anion, is stabilized by multiple bond. So this pi bond is formed by p pi d pi overlap. Because of this stabilization of this oxo ion by p pi d pi, means electron from filled orbital of p orbital of octane is transferred to the vacant d orbital of sulfur, resulting in the formation of p pi d pi. Because of this p pi d pi formation, the oxo anions are stabilized. So all the oxo anions of group 16 are stabilized by this p pi d pi type back bonding. So because of this is being stabilized. So this is the oxo acids of group 16, that is mainly the sulfur. Now coming to next, that is oxides of sulfur. Oxides of sulfur. Now sulfur has got two oxides, that is sulfur dioxide and sulfur trioxide. So let's discuss some of the properties of this sulfur dioxide and trioxide. Sulfur dioxide, the central atom sulfur undergoes sp2 hybridization, and the structure is sulfur oxygen with a lone pair. So this is an sp2 with a lone pair. So because of this bond angle is less than 120, which was supposed to be 120, but we have less than 120 because of this lone pair bond pair repulsion. So we have this sulfur dioxide. This sulfur dioxide, majority of this sulfur dioxide, 99% of this sulfur dioxide is used for preparation of sulfur trioxide, that is used in the contact process. So the main purpose of this sulfur dioxide is to convert it into sulfur trioxide, which is further used for preparation of sulfuric acid in contact process. So this is hybridization. Shape is V shape or bend or angular. Geometry is plane, triangular, or simply we say planar. Bond angle is less than 120 because of this lone pair bond pair repulsion, and due to the presence of this lone pair, this can act as a nucleophile. Though we have two options which is attached to sulfur, because of this electron withdrawing, we can say that this will be an electrophile, but we also have a lone pair electron. Because of this lone pair, this sulfur dioxide will act as a nucleophile or nucleophilic character. Now this sulfur dioxide shows reducing character, or we say this is bleaching agent, as a bleaching agent. So we'll just tell why sulfur dioxide acts as a bleaching agent. Bleaching means to fade the color. The bleaching action of this sulfur dioxide is due to its reducing nature, not due to oxidizing agent nature, but this is due to its reducing nature. And the bleaching action of sulfur dioxide is temporary. that means on keeping for some time, again the color appears. So let me explain here. This sulfur dioxide, when dissolved in water, this gives you sulfuric acid and this gives you nascent hydrogen. This nascent hydrogen is responsible for its reducing nature. So we have X, that is color substance. This color substance reacts with this active hydrogen when this is converted in X. So this is colorless. So now look at this. When this colorless substance or the reduced species is exposed to atmospheric oxygen, the oxygen present in atmosphere is again reoxidized to give you, so again color appears. So because of this we say this is temporary in nature. So first thing is the bleaching action of sulfur dioxide is due to its reducing nature. This is the reaction, and whereas this is temporary because the colorless phase when exposed to atmosphere the color reappears, that is due to reoxidation by atmospheric oxygen. Now coming to the taste for sulfur dioxide, first we can taste by smell, that is choking smell, that is smell of burning sulfur. Second taste, that is a chemical taste. Now this sulfur dioxide, when sulfur dioxide gas is passed through acidified potassium dichromate solution, color changes from orange to green. So we have look at this K2Cr2O7 plus acid plus sulfur dioxide. So chromium is plus 6, sulfur is plus 4. So this is reducing agent, this is oxidizing agent. When this reacts to give you potassium sulfate, chromium sulfate. So chromium changing from plus 6 to plus 3. So this chromium sulfate, chromium in plus 3 is green color. This is orange. So this reaction is due to nothing but reducing agent, oxidizing agent reaction. So when acidified dichromate solution, to this acidified dichromate solution we pass sulfur dioxide gas, color changes from yellow to green. Green is due to formation of potassium sulfate. So this chromium sulfate, chromium plus 6 state plus 3 state shows green color. That is one of the taste. The second taste is starch iodide taste. Starch iodide taste. We have potassium iodide KiO3. To this we sulfur dioxide gas and starch is added. So this is oxidizing agent, this is reducing agent. So this reduces to give you iodine. So this iodine absorbs on the surface of starch and gives you this iodine getting absorbed on the surface of starch gives you violet color. So the starch iodide complex forms violet color. So look at this formation of violet color when this colorless substance sulfur dioxide is passed gives you starch iodide complex which gives you violet. So these are the three tests by which we can taste or check the presence of sulfur dioxide. Then the next is sulfur trioxide. So in this sulfur trioxide, this sulfur is again undergoing sp2 hybridization. So this is planar, we have this structure. So this sulfur trioxide, due to the presence of 3 electron withdrawing oxygen, this sulfur is electrophilic in nature. So in sulfur trioxide, sulfur is electrophilic. In sulfur dioxide, sulfur is nucleophilic in nature. As I have told you, this is mainly produced from sulfur dioxide, when this gives you sulfur trioxide. And this sulfur trioxide is used for preparation of sulfuric acid in the contact process. At room temperature, this exists as solid as well as gases. So gases is, we have this structure. So in solid state, this exists in monomeric polymeric form, cyclic structure or polymeric structure. So we have this cyclic trimer, or we can have polymeric, so we can have this polymeric structure also. So in solid state, either this exists as cyclic trimeric form or polymeric chain form, and majority of this sulfur trioxide is used in preparation of sulfuric acid. So if you look at it, this is again, this pi bond is stabilized by p by d pi bond. So these are some of the important compounds of group 16, their general properties and their chemical properties. Thank you.